The human fascination about agile flying beings like birds and bees have propelled decades of research on trying to solve the problem of obstacle avoidance on aerial robots. However, most of the prior research has focused on static obstacle avoidance. Albeit, in nature, a bird's real life is very different. You often encounter predators or your not-so-friendly neighbor trying to attack you. To solve the problem of dodging, these masters of flight have evolved to sense at high speed with low latency even at night. Our Intel Aero quadrotor is equipped with a front and down-facing event camera, a down-facing sonar, and an IMU to achieve the task of dynamic obstacle avoidance using onboard sensing, and all the computation is run onboard an NVIDIA Jetson TX2 without the use of any motion capture system. To achieve dodging dynamic obstacles, we utilize a class of sensors designed by drawing inspiration from nature to excel at such tasks. These event cameras only collect the asynchronous intensity changes in light instead of traditional image frames, thereby enabling high-speed computation and fast reaction times. To realize such a bio-inspired dodging solution, one could train a deep neural network-based solution, but such a system suffers from high computational cost and a need for a lot of data. Obtaining such data from the real world is arduous, expensive, and time-consuming. Instead, we simulate objects flying at our drones and learn a series of shallow neural networks for the complete navigation stack of flying and dodging dynamic obstacles. All our neural networks are trained in simulation. However, the real data looks very different from the simulation as it suffers from noise, which is hard to model. Instead of making the neural networks larger to make them resilient to noise at every stage, we propose to use a shallow neural network for pre-processing the raw event frames to remove noise and motion blur. We call this EVDodgeNet. Now, assuming the down-facing camera is looking at a near planar surface, we estimate the odometry using a combination of the sonar and the EV homography net. Later, this odometry is used to warp the front-facing event frames to perform motion compensation such that the dynamic obstacles stand out, which is finally fed into the EV segflownet to obtain segmentation flow. This information is then fed into our control policy to find a safe direction or trajectory to avoid the dynamic obstacles. We successfully evaluate and demonstrate the proposed approach in many real-world experiments with obstacles of different shapes and sizes. To our knowledge, this is the first deep learning-based solution to the problem of dynamic obstacle avoidance using event cameras on a quadrotor. We also apply the proposed strategy to evade fast dynamic obstacles such as drones and territorial birds. By merely reversing the control policy, we can also accomplish the pursuit task, proving that our navigation stack can cater to different scenarios. Also, the most impressive part about our research is that we only train our models on simulation, which directly transfer to the real world without any fine-tuning, which highlights the generalizability of our networks. Finally, our code is open source to accelerate further research, and we encourage you to have a look at it.